China recently carried out a test that, on the surface, looked like another smooth step toward its planned moon missions. The flight involved a next-generation crew spacecraft and a test booster linked to the country's future lunar architecture. By most visible measures, the operation worked. The vehicle flew its profile, reached space, and completed a demanding return sequence. But behind that apparently clean result, there was a small issue during the booster phase that did not end the mission, yet still matters. Not because it caused a failure, but because it happened during a test meant to reflect real mission conditions. And when a country is building a system for sending astronauts toward the moon, even a minor irregularity can reveal a lot about what still needs to be proven. So let's take a closer look. If you value clear grounded space coverage without the noise, this channel is built for that. The event at the center of this discussion was a recent test flight conducted by China as part of its developing lunar exploration system. The test combined two important elements: the Mengzhou crew spacecraft, which is being developed as China's next-generation vehicle for human spaceflight, and a Long March 10A test booster, a prototype related to the heavy lift rocket expected to support future lunar missions. During the test, the booster lifted off and followed a suborbital trajectory that carried it slightly beyond the Kármán line, which lies about 100 kilometers above Earth and is widely used as the boundary of space. The vehicle reached an altitude of roughly 105 kilometers, placing it just inside the space environment before beginning its descent sequence. This test was designed to simulate several parts of a real mission profile. One of those elements involved a controlled return maneuver, similar to what a reusable rocket stage might perform while descending back toward Earth. As part of that process, grid fins, small aerodynamic control surfaces mounted on the booster, were supposed to deploy and help guide the vehicle during the atmospheric phase of the return. However, during this stage of the flight, one of the grid fins did not fully deploy. As a precaution, the onboard flight computer kept the opposite fin folded as well. Even with that unexpected situation, the booster maintained control, continued toward its recovery point at sea, and completed the planned test profile. To understand why this test matters, it helps to first look at what engineers were actually trying to verify during the flight. The mission was not simply about sending a booster to the edge of space. Its main objective was to test a specific safety scenario that could occur during a real launch of a crewed spacecraft. That scenario is known as a maximum dynamic pressure escape, often shortened to max-Q escape. During a rocket launch, the vehicle passes through several different phases of flight. At first, it moves relatively slowly, but remains deep in the atmosphere where the air is dense. Later, it accelerates rapidly while climbing higher, where the air becomes thinner. Between these two phases, there is a point where the combination of speed and atmospheric density produces the strongest aerodynamic forces on the rocket. This moment is called maximum dynamic pressure, or max-Q. In simple terms, it is the point where the rocket experiences the greatest stress from the surrounding air. If an emergency were to occur during this exact moment, such as a major failure in the rocket, the crew spacecraft would need to separate immediately and escape safely. Testing that capability is extremely important because it represents one of the most demanding situations a spacecraft safety system could face. But performing such an escape is not as simple as pressing a single button. A max-Q escape requires a very precise sequence of automated actions. Engineers often describe this sequence as a chain of commands that must occur within a fraction of a second. In some cases, dozens of operations, sometimes close to 100, must be executed within a single second. These operations include several critical steps. One of the first is pyrotechnic separation. This refers to small explosive devices designed to instantly detach the spacecraft from the rocket. These devices must fire at the exact moment required, because separating too early or too late could destabilize both vehicles. Another step involves switching the spacecraft's power systems. While attached to the rocket, a spacecraft may rely on power supplied through the launch vehicle. During an escape, the spacecraft must immediately transition to its own internal power source. If the sequence happens in the wrong order, for example, if separation occurs before the power system switches over, the spacecraft could briefly lose electrical power. Even a delay, measured in milliseconds, can be significant in this environment. The complexity increases further because, during an escape scenario, both the rocket and the spacecraft are still moving together at high speed. The rocket engines may still be firing while the spacecraft activates its escape motor. The spacecraft's escape system is essentially a powerful rocket motor designed to pull the crew capsule rapidly away from the failing booster. When it ignites, it generates a strong thrust that quickly increases the distance between the two vehicles. However, engineers must carefully calculate how the spacecraft moves relative to the rocket. They need to ensure that the capsule does not collide with the booster, and that the rocket's exhaust plume does not interfere with the escape trajectory. This is where the booster's grid fins also become important. Grid fins are lattice-shaped aerodynamic control surfaces mounted on the sides of a rocket stage. Unlike traditional flat fins, grid fins allow airflow to pass through their structure, which helps maintain stability during high-speed descent through the atmosphere. They are commonly used on rockets designed to control their orientation during re-entry or landing maneuvers. In this test flight, 2 grid fins were supposed to deploy to guide the booster during its simulated return. When one of them did not fully deploy, the flight computer responded conservatively by keeping the opposite fin folded as well. This decision helped maintain balance, preventing uneven aerodynamic forces from affecting the booster's control. Even with that unexpected condition, the vehicle continued to guide itself toward its recovery ship. As part of the demonstration, the booster performed a hover maneuver roughly 5 meters above the ocean surface, showing that its guidance system could maintain precise control near the end of the flight. After the booster touched the water, the upper boilerplate section, essentially a non-functional structural component used for testing, broke away during the splashdown impact. The lower section of the vehicle, which contained the propellant tanks and 5 working YF-100K engines, remained intact and was later recovered for inspection. Recovering this hardware is a critical part of the testing process. Engineers can examine the engines, tanks, and structural components to see how they behaved under real flight conditions. This data helps confirm whether the vehicle performed as expected and whether any adjustments will be needed before future missions. At first glance, a single booster test with a minor anomaly might seem like a small event, but within the broader context of China's space program, it connects directly to a much larger objective: sending astronauts to the moon. For that goal, China is developing a new launch system centered around the Long March 10 rocket. This vehicle is designed as a super heavy launch system, meaning it can lift extremely large payloads into space. Current projections suggest the rocket could deliver roughly 70 metric tons to low Earth orbit, and about 27 metric tons toward the moon on a lunar transfer trajectory. Those numbers matter because they define what kinds of missions become possible. A crewed lunar mission requires not only a spacecraft for astronauts, but also life support systems, propulsion modules, and a lunar lander capable of traveling between lunar orbit and the surface. All of that mass must first be launched from Earth. In China's planned mission architecture, the process would likely involve 2 separate launches. One rocket would send the crew spacecraft toward lunar orbit, while another would launch the lunar lander. Once both vehicles arrive near the moon, they would rendezvous and dock. The astronauts would then transfer into the lander, descend to the lunar surface, and later return to orbit to rejoin the main spacecraft. This approach is designed to reduce the amount of mass that must be lifted in a single launch, which can simplify certain engineering constraints. Alongside the rocket, China is also developing the Mengzhou crew spacecraft. This vehicle is intended to replace the current Shenzhou spacecraft for future deep space missions. While Shenzhou was designed primarily for missions in low Earth orbit, Mengzhou is expected to support longer and more demanding flights, including those that travel beyond Earth's immediate orbital environment. The design places strong emphasis on reliability and safety, two critical requirements for any human spaceflight system. Engineers have also explored ways to make parts of the spacecraft reusable, which could reduce long-term operational costs. All of these developments are tied to a long-term strategy that China formally outlined years ago. The country's lunar exploration roadmap has been structured in three broad phases. The first phase focused on robotic exploration, including lunar orbiters, landers, and sample return missions. That stage produced several milestones, including the Chang'e 5 mission, which successfully returned lunar samples to Earth in 2020. The second phase is centered on achieving a crewed lunar landing, which Chinese officials have indicated could take place before 2030 if development proceeds as planned. Beyond that lies a third phase involving the creation of a more permanent infrastructure around the Moon. One proposed concept is an international lunar research station, envisioned as a platform supporting both robotic and human activities on the lunar surface over extended periods. If these plans progress successfully, the technologies now being tested, such as heavy launch vehicles, new crew spacecraft, and lunar landers, would form the foundation for sustained lunar exploration. Although the recent booster test achieved most of its objectives, several aspects still require closer analysis. The grid fin deployment anomaly, while relatively minor, is one example. Engineers will need to review telemetry data and physical hardware from the recovered booster to determine exactly why the fin did not fully deploy and whether the issue was mechanical, procedural, or related to the testing configuration. This type of investigation is routine in aerospace development. Early test flights are specifically designed to expose small irregularities before a system moves closer to operational missions. If the root cause is confirmed and resolved, it could help improve reliability in later versions of the launch vehicle. At the same time, testing is continuing on other parts of China's lunar architecture. The Mengzhou crew spacecraft, which participated in the recent mission, is expected to undergo additional trials in the waters near Hainan. These upcoming tests focus on how the capsule behaves after splashdown. Engineers want to understand how stable the vehicle remains while floating in different sea conditions, and how effectively recovery teams can secure and retrieve it. The spacecraft being tested has already gone through multiple development steps, including airdrop tests and earlier escape system demonstrations. Reusing the same capsule across several experiments allows engineers to compare results from different environments and better evaluate how the design performs under repeated stress. Meanwhile, the larger systems required for a crewed lunar mission, such as the Long March 10 rocket and the lunar lander, will continue moving through their own development milestones. Each new test adds more information about how these vehicles behave under realistic conditions. For observers of spaceflight, the key point is that the process is still unfolding. Launch systems, spacecraft, and mission profiles are gradually being validated through a sequence of experiments, each designed to answer specific technical questions. And as more of those tests take place in the coming years, they will reveal how quickly the broader goal of a crewed lunar mission is moving from planning toward execution. If you're interested in following how these developments continue to evolve, future updates will likely bring new data and new milestones as the program progresses.